Okay, there's a p type. So here shall we put negative sign? We are not going to show that silicon. Okay, that is what you have to notice here. Only donor ion and acceptor ions. That will be visible for us. Silicon atoms, we are not going to show it. Holes, free electrons, and donor and acceptor ions. Only that is what we are going to. And don't need not to show that covalent bond. That also you leave it here. So here holes will be there. There's a base diagram which will carry on for the total chapter for whole 1 week. Except in logic gates, everywhere I'll be using this one. This everything is there in molten state. And now what will happen to the system? So here are few minority carriers, I show it. Okay, keep it here. So there's a p type and n type. Fine. Okay, now what will happen? The diffusion will occur. The majority carriers are here, the electrons in the n type, and they will diffuse from n to p type. Similarly, the majority carriers in the p type are holes, they'll diffuse from p to n type. When they're moving, why the diffusion occurs? It's a natural phenomenon. Region of displacement of molecules from region from higher to lower concentration. That's what happens here. So let's not bother why diffusion occurs. The diffusion occurs because of concentration level, difference in concentration level. So as it propagates now what will occur here now? These electrons when they are moving, so it will encounter hole, no? And when hole captures free electron, what do you get? I think there's a previous class we have made it. We get and that valence electrons we don't show it, or you go for energy band diagram. If an electron makes a, if there's a hole and if there's a free electron, if a free electron makes a transition, tell me like if electron makes a transition from higher level to lower level, go back to hydrogen spectrum, it will give out energy, no? This energy what will be absorbed by the material itself here. So when the electron is captured, when the free electron is captured by the hole, what do we get? We get valence electron. That valence electron we don't show here. But what happened? The energy got decreased. So where do that energy go? Will be absorbed by the material itself. There's a photon. Photon is photon. This one. This photon open is energy. They'll be absorbed by the material itself, and it's converted into heat. This is what happens in semiconductor material. So when I do like this, so initially what happened? Due to diffusion, these electrons they'll move in here, and similarly the holes also will move. I told you like so if you're getting confusion, only take displacement of electron, but actually both holes and electrons they will diffuse here. Why they diffuse? Due to concentration level, nothing, no other reason. So they'll start diffusing. So when the holes will move from p to n type, here n type all majority carriers electrons. So then what when the holes will become minority, so they'll be captured by electrons. When the electrons move from n to p type, the moment they enter into p type, they'll become minority and they'll be captured by the holes electron. So like that what happen? This is a junction. This particular thing is called a junction or a boundary. So at this particular junction, so what will happen to this donor ions? There's a donor ion. I'll be using word frequently. Donor ion. And what is this? Acceptor ion. And what will happen to those ions which are nearby the junction? Shall I say they are being robbed of their majority carriers? They lose their majority carrier. And because of that, a net charge layer will be developed here. So finally, after when the diffusion occurs, I think I'll go for next page. What do we get because of this? This will be robbed off. They will lose what, like the majority carriers. What is the type of layer we'll get it? That electron minority carriers, keep it like this one, no problem. Yeah. So we'll get a layer, no? So here, look at that layer, no? So shall I say some charge layer is being like obtained, this one, and there's a positive charge layer is built up on the N type and negative charge layer is built up on the P type here. So there's a P type. I think I'll write it inside. There's a P type. This is N type. How long, or means now you can say further no more diffusion occurs. Why the diffusion stops? That's what we have to give explanation. So as initially what will happen, the majority carriers will move from one region to another region. The electrons will move from P to N type, O's will move from N to I type. So where the recombination will occur here or nearby the junction. The recombination will occur nearby junction. What is the recombination? Already I gave diagram. Okay, just remember. Recombination valence, and that valence electrons we need not to show in this region. No, as like this, the diffusion continues. Then at one instant what happen? A charged layer means as one instant open, the diffusion stops here. Why the diffusion stops? You get the electric field now. There's a positive, go back to electrostatic, there's a positive charge there, negative charge there. How the electric field will be always from positive charge there to negative charge there. So here we'll get an electric field. For better learning, you show that E bar very clearly in the book, in your notebook. Those who are writing, no, this E bar should be visible. Okay, this is electric field. Let's come for electron. If an electron in an electric field, there's a E bar. If any electron is present, tell me what direction it will experience a force. Electron shall I show like a this one. So in what direction will experience force? Towards right, Fe. And if any hole is present, what direction the hole? Hole will experience force towards left. Any reason? Because only the positive charge will experience force in the direction of field. Go back to electrostatics, and the electron is the negative charge will experience force in the opposite to electric field. Now this particular electron now is a majority carrier. it is having enough energy. It wants to cross. The moment it enters here, it's having kinetic energy. With that kinetic energy, it wants to go. So what this electrostatic force will do? Will repel it back because it will not have enough kinetic energy to cross over to the P type. So what about this electron? All electrons, most of the electrons open, they don't have sufficient energy to cross over the layer. So this particular layer, I'll call it as a depletion layer. We'll give some name, depletion. Why the name? Yeah, most of you, I think some of you are very good in English. Depletion. If we start eating like this every day, okay, two breakfast, one lunch, one dinner, the resources will get depleted, and for future generation, there won't be enough food. What means depletion? Will be robbed off. So what we are doing now, we are depleting the resources. No, shall I use word depletion? Depleting. We are depleting resources. See, using is different, depleting is different. Using means as how much needed you are using, but we are not doing like that. We are depleting the resources. Electricity, even night also open. Well, most of the lights will be on. So we are wasting energy, no, nothing but we are depleting the energy, that one. So coming generations, yes, definitely the resources will come down. They have to fight for resources. They have to fight for water, everything. Already now fight for water started. So like this, depletion means robbed off. We are robbing off the resources. So what we are thinking is like, okay, now with my intellectual power, I earned it. Okay, whatever you earn, what pen, you don't have a rule to eat so much. Because coming generation, what they should eat, because everything comes equal to mc square. What all mass is there, what all the resources that are coming is nothing but mass, no? From where that will come energy. And when earth is created is having some energy. So with every passing day, what happens as you start consuming resources, mass is decreasing. So the energy of the earth will get converted to mass, and that mass we are putting. So indirectly, what happens, we are decreasing energy. One fine day, there won't be energy left over to convert into mass. Finish all. These are the very long-term basis. Huh? We have a lot of problems. Okay, like this, depletion means robbed off. So why robbed off? The majority carriers are being the ions are being robbed off of their majority carriers. So these ions they are not lost. Forcibly what happens? This electron open when it is moving from N to the moment it enters into P type, it will be the hole will capture it. So this particular ion open lost its majority carrier. No? Similarly, hole when it moves from P to N type, it will capture the electron. So it is being robbed. This ion it is being robbed off. So therefore, being robbed off or being depleted, we'll call it depletion layer. So what is the depletion? I went to river for river bath. My clothes are being depleted. I think all of you understood. Robbed off, no? Then you have to be in the river till somebody comes and supplies clothes. So some novels you can see that one. I'm being depleted, or when you see some movies, no, they say like in Western movies, no, like I'm being depleted. I'm being depleted. They use word means I'm being robbed off. Depletion means they don't give ease on their own. They're not surrendering. They're being robbed off here. Like this, what is the depletion layer? Shall I say it's a charged layer? What about the E? What about the charge density will be non-uniform? Some regarding depletion layer will put it. What about the charge density here? Sigma. Shall I put sigma? Non-uniform. In the diagram appears uniform. Basically, it will be non-uniform. Non-uniform charge density. On the n type, okay, this is the n type. No, on n type, positive charge layer is built up. This is the n type. No, okay, already we written. So here also let me write this n type. On p type, negative charge layer is built up. Okay, fine. So this is what happens here. So now, what is the this bias potential? Means like what is the thickness? Thickness will be of order micrometer, few micrometers. So let me put 3 into 10 to the power of minus 6 meter. That is what the depletion layer thickness. And if you go and check it, no thickness and a potential difference is set up. So how much potential barrier? So if you check it, the potential barrier will be 0.7 volt for silicon, 0.4 volt will be for this one. Potential barrier means this one. I'll measure the potential difference and how much it will be. Potential barrier is a potential barrier due to for what? For majority carriers, because this electron wants to move from N to P type because here more electrons, less electrons. What the depletion will oppose? So shall I say a barrier is formed? So what is this potential barrier? So when you substitute all, check it, no, the electric field will be of order how much? Will be of order 10 to the power of 6 volt per meter. It's a very high electric field. No? The thickness will be of order few micrometer, and the potential difference when I go and measure, no, 0.7 volt. So barrier for what? Barrier for majority carriers. This electric field will not permit the electrons to move from N to P type, or it will not permit the hole to move from like a P to N type here. But practically what we see, there are some most energetic electrons are there. How do they become most energetic? Due to thermal agitation. Due to thermal agitation, some of the electrons, what happen, most energetic electrons, they will move from like this, and they'll be captured here. Oh. I'll show by red color. They'll be captured here. And the moment it enters here, it will undergo recombination. Similarly, a most energetic hole, most energetic hole will move this one. No, not all, most energetic. So what is this? There'll be a moment of most energetic hole. How from N to P type here. Majority carriers, most energetic majority carriers only are able to penetrate depletion and they'll reach here. The moment they come here, they'll undergo recombination. Means sir, one fine day, there won't be electrons left over, and there won't be holes left over, because that's what the way you are saying. Yes, what is the here again? There'll be breaking and making up of covalent bond will take place due to thermal agitation. These are some very important ideas. I'm going to put it here. Due to thermal agitation, I think, yeah, we'll write it here. No, this is the covalent bond. No, I'll show silicon like this, and this is the valence electron. Due to thermal agitation, they will get some energy, thermal energy. Because silicon, when they vibrate, so these valence electrons, they get sufficient energy, they'll break up. Means covalent bond break up means it'll break up and will become powder. Not like that. The bond will be there. Only the electrons, what happen? They'll get liberated. If electrons get liberated, what do we get? The vacancy created by valence electron in valence band, hole, and will get the free electrons. So how do this particular electron which is lost, which will diffuse, most energetic electron moves from N to P type, not all, most energetic electron. How do it will be brought back? So here what happen? Covalent bond will break up here. The making and breaking up of covalent bond will occur in both P type, N type, and depletion layer. Here, why do that covalent bond will break up? Due to thermal agitation. So here I'll put it, covalent bond breaks up in P type, N type, and in depletion layer. Making and breaking up, covalent bond breaks up. Making also will occur. Later on I'll write that sense. Time being okay, that one. So the electron which is lost here, what happen? How did it is brought back? Due to breaking up of covalent bond. Let's assume that 2 electrons has moved here. So 2 O's and 2 electrons are lost, no majority carriers. From where do it has come? One covalent bond breaks up here. So 2 electrons are generated. So that will take place here. And the 2 O's which were lost here, that will come from here. So for here open, for every displacement, making and breaking will occur here. So like this, the most energetic, that one means, like if you take the diode PN junction here, so is there any current? There's a current, no? What direction that current is? The current is in this direction. And what is this current? High diffusion. I'll take it out all this because I had to, I'll show it. In another diagram, I'll show it, small diagram. Okay, this diffusion current. So why do this? This is due to what? Due to moment of most energetic majority carriers. Why do this? Due to moment of most energetic electrons from N type to N type and the holes P type to N type. Okay, there's a reason for this current what I'm putting. Not all, only due to most energetic this one. So due to that there'll be current. So now practically if I go and check, there is no such a diffusion current. The net current is zero. Let me say net current is zero. But according to the explanation what I'm giving, there is a current is there. But practically go and check it, the net current is zero. There should be some other current which is equivalent opposite to this will be flowing. Why? How that is means? There'll be breaking up of covalent bond. First we'll go for only breaking up. Then I'll say that how that making up will take place. So there'll be breaking up of covalent bond will occur here also. Breaking up of covalent bond will occur here also. When covalent bond breaks up here, so what do we get? We get one. I'll show it. Now holes will be generated. That hole, can it be anywhere? It can break up. The covalent bond can break up either here or here. I'm just took this one. So and these are the free electrons. If one covalent bond breaks up, when two electrons, two holes will be generated. And this electron in what direction will experience a force? Will experience force towards right. And this electron, shall I say, it will move like this. Any color? Okay, green color will take it. Minority carrier, I'll show by green color. Okay, look at that red and this one. And what happens this hole? How do it will move? It will move in this direction. What is this green color? Minority carriers, no? And what about that red and blue? That was majority carriers. So now here, if a covalent bond breaks up, electron what happens because of electric field experience force towards right. Either covalent bond breaks up here or here. Things are same. I'll do one thing for your understanding purpose. I'll show it here also. Tell me like this all, how do it will move? Because of electrostatic force, it will move like this. What about this electron? It will start moving from here. Okay, got the idea now? So any minority carrier, shall I say that, sir, why you are calling minority carrier? First of all, you have asked one very beautiful question here. So why you are calling them as minority carrier? Okay, now let's come for this. Forget depletion layer, come for this one. Here what happened? What is this electron? Minority carrier, no? This electron is a minority. All of you just come to the region where I'm looking at, I'm just writing some star mark, you know, they're the minority carrier, will I agree? What is the state of this? Due to thermal agitation, this will be moving randomly, this minority carrier. That one. So now what happened? By chance, when it is moving like this, by chance, if it enters depletion layer, what depletion will do? Will exert a force, no? Will accelerate it, will drift it, or will start pulling it, no? It will hold electron, it will hold collar of electron, and it will hold the arm of electron, and it will drag him, the depletion layer, this electrostatic field. By chance, this electron, which will be moving randomly, the moment it enters here, what this electrostatic field will push him, will just pull him, and will place him in N type. Getting this one, same thing happens all. But by chance, what happened? The hole. So this what happened is moving. Let's assume that this hole is moving here. The by chance what happened? If the moment it enters here, what this depletion will do? Will drift him, will push him to P type here. So now look at this electron. This electron. So this electron either generated here or here. How it will move? Towards right. The hole either generated here or here. How it will move? Towards left. If any hole, this hole, the minority in N type, by chance enters depletion, will be pushed like this, no? So here is what I'll show this one. This will be the green color only, I'll show it. So it will be like this. I'll show that arrow, so that will be easy for you. So therefore now any carriers that are generated either due to breaking up of covalent bond in the depletion layer, the electrons and the holes which are generated, shall I call them as minority carrier? Because they're having a displacement similar to this holes in the N type. They're having a moment similar to the electrons in the P type. And now look at this. Let's talk about the current here now. This whole current will come and electron current, and the electron flows here. So tell me this minority carrier current in what direction? Will be towards left. Shall I put one more here? The drift current. Now we have to give reason why this drift current is. Due to moment of minority carriers. What are minority carriers? The holes from the N type will move from P type, and the electrons from P type will move to the N type here. This was due to minority carrier. So what is the drift current? Why the drift word? Because they are being forced to know. Say what all wants to move here. So look at the electron. It wants to move. But the moment it enters, it will be pulled towards the n-type. So it is being drifted. It is being forced to move from p to n-type, this minority carrier. So therefore, this is a minority carrier current. So now if you see the practically the p-n junction, the diffusion current and the drift current will be equal and opposite. So therefore, the net current to the p-n junction will be 0. This is a core idea. How all our the whole week discussion will just revolve around this condition only. Just like a story, you have to put in a order, nothing else is there. You don't go for any equation, nothing. Now let's come for that one. So like this here, covalent bonds, if they keep on break up, if they keep on break up, finally one day there won't be covalent bond to break up, then no drift current. But making and breaking up of covalent bond will occur in all the regions, in n-type, p-type, depletion layer also. So I'll put it here. Making and breaking. There's one very best statement is what I'm putting here. So shall I put here making and breaking? I think I'll write it here. Making and breaking up of covalent bond occurs in n-type, p-type, and in depletion layer at all times. Like this, no, this semiconductor weapon continues with this making, breaking. Okay, the breaking, why the breaking occurs? Due to thermal agitation. Why breaking occurs? Covalent bond breaks up in p-type, n-type, and depletion layer due to even makeup. How that makeup will occur? Okay, let's come for in p-type the covalent bond breakup. How do that makeup will occur? Suppose one covalent bond breakup means, okay, this one, this particular hole what happen, it moves from n to p to n-type, it has lost. Or let's assume two holes from p to n-type, they have moved it here, and their recombination occurs here. Two electrons are lost, two holes are lost. Then from the holes which are lost, how do here covalent bond will break up? Then that two holes will be generated here. Then next again here what will happen? Here covalent bond will break up. The electrons two holes will be lost. Here two holes are there. No, that two holes open will become minority, and they'll move like this. They'll come here. Clear this one. And here open one covalent bond has broken. No? Due to that what happened? Two valence electrons are lost, and these two electrons when they come here what happen? When they combine with what like the free electrons which are minority carriers, no, the two holes which they come here. So again it will get back to its original valence electron. I think I'm just explaining statement because I can't give much diagram. Suppose say here, let's assume that two holes have moved here. Two electrons are lost. Recombination, two valence electrons came. Covalent bond will break up. The same two valence covalent bond breaks up. Here what happened? Two electrons and two holes are generated. The two electrons which are lost, okay, got back. The two holes which are generated, what they do? They will move because they're minority carrier, and they'll come and settle here. Like this, what happened? You can give suitable reason. So making and breaking up of covalent bond will take place all the time at all points. Okay, here making breaking occurs like this. Means, sir, this electron, can it be captured by this? Yes, it can happen. This hole, even that also possible. Okay, which we are not interested. So this particular electron when moving can be captured by this hole. Yes, it happens, but we are not bothered. It's of no use for us. Okay, now here breaking occurs. Due to breaking occurs, minority carriers are generated. Let's assume that one. What about making? Who will make this? Okay, the majority carriers. This when they are moving. Okay, this majority carrier when it is moving, open, it can be captured by this hole. Suppose here one covalent bond has broken up. Two electrons. That electrons they'll go like this. The holes will go like this here. Then the holes will move like this. So sorry, holes from here they'll be moving like that. And the electrons will be moving. These electrons, when they, sorry, like majority carrier, no, sorry. If a covalent bond breaks up here, two electrons, two holes be generated. That whole certain will move like this, electrons will move. They're the minority carrier. How the making up occurs? Suppose a covalent bond has broken up. The majority carrier which is moving here will be captured by this hole. Clear this? And the majority carrier which is moving here in depletion will be captured by this particular electron. So like that happen, the making and breaking up of covalent bond will take place. We are not bothered about making up of covalent bond, the depletion layer, which is of no use. That's why in the books open, they avoided this discussion. So I'm just putting one statement. You need not to bother anything here now. Just only thing is try to focus on this one. Drift time, the diffusion current. Why the diffusion current? Due to movement of most energetic holes from P to N type, most energetic electrons from N to P type. Why minority carriers? Due to breaking up of covalent bond in the depletion layer, the carriers which are generated, they are minority. Means either covalent bond breaks up here or here, they'll become minority. Don't think that these electrons are N-type majority. No. This again, it's like a this electron generated here. How did it move? From like this, no? Similar to this electron. So therefore, the carriers which are generated in depletion layer due to breaking up of covalent bond, they will become minority carriers only. You have to ask question, sir. You tell me first drift current. The drift current is due to this hole or moment of this hole. Both that one. But the who will contribute more? This will contribute more. I'm making things very, very systematic and clear. This drift current is due to this hole or this hole. Due to both. But the percentage of contribution will be more due to this. Because millions of covalent bonds will break up. And the net current through the junction will be zero. High diffusion equal to high drift. I think there are so many things are happening. So for your level, I suggest you like drift current, diffusion current. Diffusion current is due to movement of majority carriers across the junction. Drift current is due to movement of minority carriers. How that minority carriers are? Due to breaking up of covalent bonds in the depletion layer. Got the idea? So therefore, now PN junction. So altogether, net current to a PN junction will be zero. Unbiased means I'm not connecting to any cell. No, I diffusion will be called I drift. So net flow of current PN junction is zero. Okay, clear now. So this is the breaking up of covalent bond like this. We have shown that one. Okay, let's come for this one. This is unbiased. Okay, now when I go and check it, no, there'll be a potential barrier will be there. So what is the potential difference generated? I have to show potential difference, no, here. Okay, we'll do one thing. One more diagram. In books, they are given diagram of energy level also. Just do refer once. This will be high diffusion. Let me show that. Potential barrier. What is the potential barrier? Barrier for what? Barrier for moment of majority carriers. And how much this is equal to? And the width is this one. So this barrier potential will be 0.7 volt for silicon, 0.3 volt for germanium. How much of energy they needed for the electron, most energetic electron, how much of energy needed? E into VB. If the most energetic electron is having energy, E into charge of electron into 0.7, yes, it can move. Any electrons whose energy is less than E into VB, it cannot move that one. So here energy of majority carriers if it is greater than E into VB. Energy of majority carriers if it is greater than EVB, they will diffuse. I think I should write in form of sentence. Then they will diffuse. Okay, fine. So it germanium or silicon. Those majority carriers whose energy is less than this, they cannot diffuse. So like that, there'll be few other, not many. Some most energetic electrons from N type will diffuse to P type, or most energetic holes will diffuse from P type. Not all. I'm making clear. Okay, then what about the this distance? This will be of order few micrometer. Not centimeter. So like this, can we calculate E? So this will be of order 10 to the power of 6 volt per meter. Very high electric field. Huh? Of order it is 10 to the power of 6 or 10 to the power of 7, anything that one. Okay, this. So this is about the potential barrier. We have put everything. What about this non-uniform charge distribution? And this is a non-ohmic. I'll write few more. Non-ohmic means it will not obey the Ohm's law here. This is the ohmic region. This layer will obey Ohm's law. Now what about the field? Field will be non-uniform. This will be charge distribution here will be non-uniform. Sigma, shall I put sigma only? Sigma again we use conductivity. No? Non-uniform charge density. I think I wrote no already. Okay, fine. Yeah. So this is about the PN junction. So many things are there. Now I'll ask you what about the potential? Which will be at higher potential? This one, no? This will be at lower potential. So if I plot the graph, how the graph will be. This will be almost at zero potential. No? So here if I go for the potential, it will rise like this. Oh, graph. So what is this? This is a potential barrier. Exactly the midpoint of junction, what is the potential? Should be non-zero, no? Here. It should be non-zero here. You know electrostatics, so what should be the potential? Here it is VB, here it is 0. So what about at midpoint? Should be non-zero, no? Look at the graph. This is 0.7. This is 0 volt. What can be this one? Should be non-zero. So what is the potential at the midpoint of depletion layer? Will be non-zero. That's what the graph is telling. Agree this? So I'm just leaving this. So you just make observation. Potential at point P. 0, non-zero. Non-zero. Energy also they have just shown in the thing, so you can refer it. Energy band diagram they're showing for N type, P type. Just go through once that one. I'll go for forward bias. This is overall about the PN junction. I think plenty of questions, if they are interested, they can ask you here. Okay, let's come for the forward bias. Doping in gaseous state is of no use.